space-based telescope even from the ground, and that's just because the star is so much smaller that the relative increase in or decrease in brightness is enhanced significantly because that's one size. So TRAPPIST-1e, it's a planet which is in the right distance for liquid water. It has a slightly smaller size than the Earth. It's about 90% the size of the Earth, about 80% mass, and it's one of the top targets right now for potentially having life. And yet, it raises many questions about what would that environment be like. This is a star which is 1/8 the mass of the Sun. It's stars like that take a long time to come off their adolescence. When stars first form, like the Sun, it takes them maybe 10 million years to sort of settle into that main sequence lifetime. But for stars like these late embryones, as we call them, they can take up to 1 billion years or more to come down. And during that period, they're producing huge amounts of X-rays, ultraviolet radiation that could potentially rip off the entire atmosphere. It may desiccate the plants in the system. And so even if water arrived by comets or something, it may have lost all that water due to this prolonged period of high activity. So we have lots of open-ended questions about these M-dwarf planets, but they are the most accessible. And so, in the near term, if we detect anything in terms of biosignatures, it's going to be one of these red dwarf stars. It's not going to be a true Earth twin, as we would recognize it as having a yellow star.
Well, let me ask you, there's a million ways to ask this question. I'm sure I'll ask it about habitable worlds. Let's just go to our own solar system. What can we learn about the planets and moons in our solar system that might contain life, whether it's Mars or some of the moons of Jupiter and Saturn? What kind of characteristics, because you said it might not need to be Earth-like, what kind of characteristics might we be looking for?
When we look for life, it's hard to define even what life is, but we can maybe do a better job in defining the sorts of things that life does. And that provides some aspects to some avenue for looking for them. Classically, conventionally, I think we thought the way to look for life was to look for oxygen. Oxygen is a byproduct of photosynthesis on this planet. We didn't always have it. Certainly if you go back to the Archean period, there was, you have this period called the Great Oxidation event where the Earth floods with oxygen for the first time and starts to saturate the oceans and then the atmosphere. And so that oxygen, if we detect it on another planet, whether it be Mars, Venus, or an exoplanet, whatever it is, that was long thought to be evidence for something doing photosynthesis. Because if you took away all the plant life on the Earth, the oxygen wouldn't just hang around here. It's a highly reactive molecule. It would oxidize things, and so in about a million years, you would probably lose all the oxygen on planet Earth. So that was conventionally how we thought we could look for life. And then we start to realize that it's not so simple because there might be other things that life does apart from photosynthesis. Certainly the vast majority of the Earth's history had no oxygen, and yet there was living things on it, so that doesn't seem like a complete test. And secondly, could there be other things that produce oxygen besides from life? A growing concern has been these false positives in biosignature work, and so one example of that would be photolysis that happens in the atmosphere. When ultraviolet light hits the upper atmosphere, it can break up water vapor, the hydrogen splits off to the oxygen. Hydrogen is a much lighter atomic species, and so it can actually escape certainly planets like the Earth's gravity. That's why we don't have any hydrogen or very little helium. And so that leaves you with the oxygen, which then oxidizes the surface, and so there could be a residual oxygen signature just due to this photolysis process. So we've been trying to generalize, and certainly in recent years there have been other suggestions, things we could look for in the solar system and beyond. Nitrous oxide, basically laughing gas, is a product of microbes. That's something that we're starting to get more interest in looking for. Methane gas in combination with other gases can be an important biosignature. Phosphine as well, and phosphine is particularly relevant to the solar system because there was a lot of interest for Venus recently. You may have heard that there was a claim of a biosignature in Venus's atmosphere. I think it was like 2 years ago now. And the judge and jury are still out on that. There was a very provocative claim and signature of a phosphine-like spectral absorption. But it could have also have been some other molecule, in particular sulfur dioxide, which is not a biosignature.
So this is a detection of gas in the atmosphere.
Yeah.
Venus, and it might be controversial on several dimensions. So, well, one, how to interpret that. Two, is there a gas? And three, is this even the right detection? Is there an error in detection?
Yeah, I mean, how much do we believe it's actually in the first place? If you do believe it, does that necessarily mean there's life there? And what gives? How can you have life in Venus's atmosphere in the first place? Because that's, been seen as like a hellhole place for imagining life. But I guess the counter to that has been that, okay, yes, the surface is a horrendous place to imagine life thriving. But as you go up in altitude, the very dense atmosphere means that there is a cloud layer where the temperature and the pressure become actually fairly similar to the surface of the Earth. And so maybe there are microbes stirring around in the clouds which are producing phosphine. At the moment, this is fascinating. It's got a lot of us reinvigorated about the prospects of going back to Venus and doing another mission there. In fact, there's now 2 NASA missions, Veritas and Dimitri, going back before 2030 or 2030s. And then we have a European mission, I think, that's slated now, and even a Chinese mission might be coming along the way as well. So we might have multiple missions going to Venus, which has long been overlooked. I mean, apart from the Soviets, there really has been very little in the way of exploration of Venus. That's certainly as compared to Mars. Mars has enjoyed most of the activity from NASA's rovers and surveys. And Mars is certainly fascinating. There's this signature of methane that has been seen there before. Again, the discussion is whether that methane is a product of biology, which is possible, something that happens on the Earth, or whether it's some geological process that we are yet to fully understand. That could be, for example, a reservoir of methane that's trapped on the surface and leaking out seasonally.
So the nice thing about Venus is if there's a giant living civilization there, it'll be airborne, so you could just fly through and collect samples.
Yeah.
With Mars and moons of Saturn and Jupiter, you're going to have to dig under to find civilizations that are living.
Right. Yeah, maybe it's easier than for Venus because certainly you can imagine just a balloon floating through the atmosphere, or a drone or something that would have the capability of just scooping up and sampling. To dig under the surface of Mars is maybe feasible-ish, with especially with something like Starship that could launch a huge digger basically to the surface, and you could just excavate away the surface. But for something like Europa, we really are still unclear about how thick the ice layer is, how you would melt through that huge and thick layer to get to the ocean, and then potentially also discussions about contamination. The problem with looking for life in the solar system, which is different from looking for life with exoplanets, is that you always run the risk of, especially if you visit there, of introducing the life yourself. Right? It's very difficult to completely exterminate every single microbe and spore on the surface of your rover, or the surface of your lander, and so there's always a risk of introducing something. I mean, to some extent, there is continuous exchange of material between the planets naturally on top of that as well, and now we're sort of accelerating that process to some degree. And so if you dig into Europa's surface, which probably is completely pristine, it's very unlikely there has been much exchange with the outside world for its subsurface ocean, you are, for the first time, potentially introducing bacteria spores into that environment that may compete or may introduce spurious signatures for the life we're looking for. And so it's almost an ethical question as to how to proceed with looking for life on those subsurface oceans. And I don't think we really have a good resolution for it as well.
Ethical. So you mean ethical in terms of concern for the preserving life elsewhere, not to murder it, as opposed to scientific work?
I mean, we always worry about a space virus, right, coming here, or some kind of external source, and we would be the source of that potential contamination.
Or the other direction.
Yeah.
I mean, whatever survives in such harsh conditions might be pretty good at surviving in all conditions. It might be a little bit more resilient and robust. It might actually take a ride on us back home.
Possibly. I mean, I'm sure that some people would be concerned about that. I think we would hopefully have some containment procedures as if we did sample return. What do you mean you don't even need a sample return? These days, you can pretty much do like a little micro laboratory to the planet to do all the experiments in situ, and then just send the planet the data. And so I don't think it's necessary that in a case like that where you might have contamination concerns that you have to bring samples back. Although if you brought back your open sushi, it would sell for quite a bit with in the
Sushi, yeah. I would love from an engineering perspective just to see all the different candidates and designs for like the scooper for Venus and the scooper for Europa and Mars. I haven't really looked deeply into how they actually, the actual engineering of the samples, because that's the engineering that is probably essential for not either destroying life or polluting it with our own microbes and so on. So that's an interesting engineering challenge. I usually, for rovers and stuff, focus on the robot, on the sort of the mobility aspect of it, on the robotics, the perception, and the movement, and the planning, and the control. But there's probably the scooper is probably where the action is.
Yeah.
The microscopic sample collection. So basically, you have to first clean your vehicle, make sure it doesn't have any earth white on it, and then you have to put it into some thing that's perfectly safe. So if we bring it back or we analyze it, it's not going to bring anything else external. Yeah, I don't know. That'd be an interesting engineering design there.
Yeah, I mean, Curiosity's been leaving these little pods on the surface quite recently. There's some neat photos you can find online. And they kind of look like lightsaber hilts. So, yeah, to me, I think I tweeted something like, this weapon is your life. Like, don't lose a Curiosity, because it's just dumping little files everywhere. And it is scooping up these things, and the intention is that in the future, there will be a sample return mission that will come and pick these up. But the engineering behind those things is so impressive. The thing that blows me away the most has been the landings. I'm trying to be a pilot at the moment, so that's the sort of, watching landings has become like my pet hobby on YouTube at the moment, and how to do it with different levels of conditions and things. But with when you land on Mars, just the light travel time effect means that there's no possibility of a human controlling that descent. And so you have to put all of your faith and your trust in the computer code or the AI or whatever it is that you put on that thing to make the correct descent. And so there's this famous period called 7 minutes of hell, where you're basically waiting for that light travel time to come back to know whether your vehicle successfully landed on the surface or not. And during that period, you know in your mind simultaneously that it is doing these multi-stages of deploying its parachute, deploying the crane, activating its jets to come down, and controlling its descent to the surface, and then the crane has to fly away so it doesn't hit the rover. And so there's a series of multi-stage points where any of them go wrong, the whole mission could go awry. And so the fact that we are very consistently able to build these machines that can do this autonomously is, to me, one of the most impressive acts of engineering that NASA have achieved.
Yes, the unfortunate fact about physics is the takeoff is easier than the landing. Yes. And you mentioned Starship. One of the incredible engineering feats that you get to see is the reusable rockets that take off, but they land using control, and they do so perfectly. And sometimes when it's synchronous, it's beautiful to see. And then with Starship, you see the chopsticks that catch the ship. I mean, there's just so much incredible engineering. But you mentioned Starships is somehow helpful here. So what's your hope with Starship? What kind of science might it enable, possibly?
There's two things. I mean, it's the launch cost itself, which is hopefully going to be per kilogram. It's going to dramatically reduce the cost. So it's the sort of even if it's a factor of 10 higher than what Elon originally promised, this is going to be a revolution for the cost to launch. That means you can do all sorts of things. You could launch large telescopes, which could be basically like JWST, but you don't even have to fold them up. JWST had this whole issue with the design that it's 6.5 meters across, and so there's no fuselage which is that large at the time. The Ares 4 wasn't large enough for that, and so they had to fold it up into this kind of complicated origami. And so a large part of the cost was figuring out how to fold it up, testing that it unfolded correctly, heated testing, and there was something like 130 fail points or something during this unfolding mechanism. And so all of us were holding our breath during that process. But if you have the ability to just launch, arbitrarily large masses, at least comparatively compared to JWST, and very large mirrors into space, you can more or less repurpose ground-based mirrors. The Hubble Space Telescope mirror and JWST mirrors are designed to be extremely lightweight, and that increased their cost significantly. They have this kind of honeycomb design on the back to try and minimize the weight. If you don't really care about weight because it's so cheap, then you can just literally grab many of the existing ground-based mirrors across telescopes across the world, 4 meter, 5 meter mirrors, and just pretty much attach them to a chassis and have your own space-based telescope. I think the Breakthrough Foundation, for instance, is an entity that has been interested in doing this sort of thing. And so that raises the prospects of having not just one WST that just, WST is a fantastic resource, but it's split between all of us. Cosmologists, star formation, astronomers, those of us studying exoplanets, those of us wanting to study, the ultra-deep fields and the origin of the first galaxies, the expansion rate of the universe. Everyone has to share this resource, but we could potentially each have one JWST each that is maybe just studying a handful of the brightest exoplanet stars and measuring their atmospheres. It's important because if we talked about this planet TRAPPIST-1e earlier, that planet, if JWST stared at it and tried to look for biosignatures, by which I mean oxygen, nitrous oxide, methane, it would take it of order of 200 transits to get even a very marginal, what we call 2.5 sigma detection of those things that we would believe with that. And 100 transits, this thing transits once every 6 days, it's sort of 4 years of staring at the same star with one telescope. There'd be some breaks, but it'd be hard to schedule much else because you have to continuously catch each one of these transits to build up your signal-to-noise. And so JWST is never going to do that. In principle, technically, JWST could technically have the capability of just about detecting a biosignature. An Earth-like planet does around a non-sunlight star, but still, we have the technology to do that. And we simply cannot dedicate all of this time to that one research. So Starship opens opportunities like that, mass producing these kinds of telescopes, which will allow us to survey for life in the universe, which of course is one of the grand goals of astronomy.
I wonder if you could speak